In today's lesson, I'm going to talk to you about how to find equilibrium concentrations, if you know the equilibrium constant and the starting concentrations. And we're going to just briefly go over LeChatelier's principle, which should be a review for a lot of you from honors. All right, our first example here is the reaction N2 plus O2 yields 2NO. All right, and the Kc for this reaction is 0.10 at 2000 degrees Celsius. So if we have a reaction mixture at 2000 degrees that initially contains 0.2 molar N2 and 0.2 molar O2, find equilibrium concentrations of the reactants and the product at this temperature. Okay, so we can just look at this and see that the Q value is going to be 0 because there are no products. So we know it has no choice but to shift toward the products. So when we do these problems, we organize them using something called an ICE table. And ICE stands for initial, change, and equilibrium. Okay, and then we will use this table to organize the initial concentrations, the change in the concentration, and then the equilibrium concentrations to solve for how much there is at equilibrium using our equilibrium constant Kc. All right, there's several examples in this lesson. I'm going to go through 2 of them in detail for you, and then the last 2 I will just give you the answers, and I want you to pause the video and attempt them on your own, and then we can go over if you have any questions in class. All right, so for this first one, our initial concentration of N2 is 0.2, and our initial concentration of O2 is 0.2, but our initial concentration of NO is 0. All right, so for every N2 that's used up, one O2 is also used up, so the change for those will be minus X for both of them, and it'll be the same amount because it's a 1-to-1 ratio in our balanced equation. And then the change for NO is going to be plus 2X because each time we use up an N2 and an O2, we make 2 NOs. Right, so you get these numbers from the balanced equation, and you have to use the coefficients. Right, so our equilibrium concentration of N2 is going to be 0.2 minus X. Equilibrium concentration of O2 is going to be 0.2 minus X, and the equilibrium concentration of NO is going to be 2X. All right, and now what we need to do is just basically some algebra. So our equilibrium expression is Kc is equal to NO squared divided by the concentration of N2 times the concentration of O2. So if we plug in the numbers from our table, we get Kc is equal to 2x, and that whole quantity is squared because there's a 2 coefficient, and then times 0.200 minus x, divided by 0.200 minus x times 0.200 minus x. All right, so the bottom quantity is really just squared. All right, so this one's not too hard because since both our top and bottom are squared, we can just take the square root of both sides and get that by itself. So, and then after we take the square root, we just do some algebra, multiply both sides by the denominator, subtract, and then solve for x, and we get 0.027 as our x. So that means, if we go back to our ICE table, that the concentration of N2 is going to be 0.200 minus 0.027, which is 0.173 molar, and the same thing for O2. And then for NO, the concentration is going to be 2 times 0.027, which is 0.054 molar. All right, and then the nice thing about these problems is you can always go back and double check your work as long as you've written your equilibrium expression correctly. So if we go back and double checked, inserting those concentrations we just found into our equilibrium expression, we get 0.054 squared divided by 0.173 squared, and that's 0.097, which is within one significant figure of our given Kc, so we can assume that we got the right answer.
All right, our second example here is consider the reaction 2H2S goes to 2H2 plus S2 gas. And the Kc for this reaction is 1.67 times 10 to the minus 7th at 800 degrees Celsius. All right, so you can already look and see that the Kc for this is very, very small, much, much less than 1, which means we're going to have almost all reactants when we're done with this, this equation. All right, so it says a 0.5 liter vessel initially contains 0.0125 moles of H2S at 800 degrees Celsius. Find the equilibrium concentrations of H2 and S2. Okay, so for this particular problem, we're going to know that we're going to have to make products because there's only reactant to start with. So we're going to go ahead and set up our ice table. All right, our initial concentration of H2S is 0.0250, and our initial concentrations of H2 and S2 are just 0. All right, and then the change for H2S is going to be negative because it's going to get used up, and it's going to be minus 2x, and the change for H2 is going to be plus 2x. All right, they both have two coefficients in our balanced equation, and then the change for S2 is just going to be plus x because it just has a coefficient of 1. All right, so our equilibrium concentrations are 0.0250 minus 2x, and 2x and x. All right, so now we're going to plug this into our equilibrium expression, which is the concentration of H2 squared times the concentration of S2 divided by the concentration of H2S squared. All right, so when we plug that in, we get 2x squared times x divided by the quantity 0.0250 minus 2x squared. Okay, so you can probably already look at this and see it's going to be much more complicated to solve this algebraically than the problem we just did. Many of you probably have the calculators that have the fancy solve button, and you can just plug this in and get x, and that's fine. You may do that this way. If you have an older calculator like me, my calculator does not do that for me. So what I do is make an approximation. So remember I said that this is going to be almost all reactants. Very little of it is actually going to react. So this minus 2x is pretty much negligible. If only a tiny amount reacts, then what we measure for the amount of H2S is going to be pretty close to unchanged. So we'll double check at the end to make sure. But as long as less than 5% of it is consumed, then our assumption can be considered valid. Right, so if we make that assumption, then we just need to solve for x cubed. That's the only other x in our equation. And then we can solve for x as 2.97 times 10 to the minus 4th. Right, and if we want to check to make sure that our x is small approximation is valid, we can take the 2.97 times 10 to the minus 4th divided by our initial concentration, which was 0.0250. And then that means only 1.19% of it reacted. So our approximation is fine because that's less than 5%. All right, so this means that our concentration of
H2 is going to be 2 times the 2.97 times 10 to the minus 4th, which is 5.94 times 10 to the minus 4th. And the concentration of S2 is going to be 2.97 times 10 to the minus 4th. Right? And then you could also plug in and solve for H2S as well, but the problem didn't ask us for that. For this example, I'm going to give you the opportunity to do it on your own. So this one is partial pressures, so your concentrations in this case will be pressures, not concentrations. And they're already in atmospheres ready for you to go. So pause here, go ahead and solve the problem, check your work, and then replay, and I can tell you what the answer is, and hopefully our answers agree. Okay, so when I did the problem out, I was able to cancel the x's because they are sufficiently small for this problem, and the pressure that I got for BRCL is 0.0103 atmospheres. So hopefully that is what you got as well, and then we'll do one more example on the next slide. All right, and then finally, this is the last one I'm going to give you as practice for this lesson. So again, go ahead, stop the video, work out the problem for yourself, draw your ice table, and then hit play again, and we'll go over what the answer is. Okay, so when I did this one, I was again able to assume that x is small, and it cancels out, and then the concentration I got for H3O plus is 0.0030 molar, so very, very small concentration. And if you have any questions about any of this, please come see me, and we're going to work through lots of problems like this in class as well. All right, and then last but not least today, I'm going to talk to you about LeChatelier's principle. So LeChatelier's principle tells us that when a chemical system in equilibrium is disturbed, the system will shift in a direction that minimizes the disturbance. Okay, so I'm basically going to go through different examples of ways we could disturb the system and explain how the system is going to respond as a result. So the first is the addition of a reactant. So if we add a reactant, now we're going to have too much on the left side of the equation, and so that's going to shift our reaction toward the products or to the right. All right, addition of a product is going to do the opposite. We're going to have to make some of that product back into reactants in order to reestablish our equilibrium. Okay, change in volume or pressure is a little bit more complicated. These both apply to gases. So if we increase the volume, obviously we're going to decrease the pressure, so they work opposite one another. And both of these are going to depend on how many gases we have in either the reactants or the products. So if we have more gas molecules in the reactants, then a change in pressure or a change in volume is most going to be effective or going to be most felt on that side of the equation. And if it's more molecules of gas on the product side, that will feel the bigger indication or bigger change. So to sum that up, if we increase the pressure or if we decrease the volume, those have the same effect, then we're going to shift toward the side with fewer moles of gas particles. And if we decrease the pressure or increase the volume, because those have the same effect, we're going to shift toward the side with more moles of gas particles. So for these, there's not just a set direction that it moves. You have to think your way through it. All right. Change in temperature is similar. So if we have an endothermic reaction, then that uses up heat to happen. So if we add heat to an endothermic reaction, then we're going to shift to the products or shift right. If, however, we have an exothermic reaction, that produces heat, and so increasing the temperature doesn't have the effect of making more products, it has the effect of making more reactants, so it will shift left, right? One way to think of this, or often a way that's thought of it, is if you think of heat as either being a product in an exothermic reaction or a reactant in an endothermic reaction. All right, and then the last is the addition of a catalyst. So if we add a catalyst, it's going to make the rate go faster, so the reaction will get to equilibrium more quickly, but the ratio of the reactants and products is not going to change. So adding catalyst has no effect on which direction the reaction is going to shift. All right, so finally we're just going to do an example. So in this one we have coal and water being used to generate carbon monoxide and hydrogen gas. So in this reaction, we have a few different things that we could do, and the first is to add more carbon. So be careful, because remember, carbon, which is a solid, will not appear in the equilibrium expression, so its concentration remains unchanged through the reaction. So adding a solid or a liquid, whether it's a reactant or a product, still has no effect on the equilibrium, so that will result in no change. All right, if we add more H2O gas, that is a reactant, so it's going to shift right toward the products. If we raise the temperature, since this is an endothermic reaction, that is going to drive the reaction forward and make more H2, so it will shift to the right. If we increase the volume, okay, here we have gas on 1 mole of gas on the reactant side and 2 moles on the product side. So if we increase the volume, overall that's going to decrease the pressure. All right, so that's going to be felt most on the side with more moles of gas, so that's going to shift toward the products as well. Okay, if we add a catalyst, remember that is going to have no effect. And then this one sometimes throws students for a loop. If we add an inert gas, all right, this isn't going to actually change anything because it doesn't change the partial pressures of each of the gases. All right, so the overall pressure in the container is going to change, but it doesn't change the partial pressures of the gases involved in the reaction. So inert means it's not involved in the reaction, so that's also going to have no change for this reaction.